I've got to try and remember which one it was. It was this one. Okay. You'll see the first page there is standard deviation and sampling. So let's recap quickly. I have, and I've probably made it a bit big for the screen. Robert, your problem. Okay, there we go. So let's assume these are plant lengths. They can be any character. It can be disease severities. It can be whatever the case may be. Okay, so these are measurements of some character, plant length. I've got 10 sampling units that make up my sample, and there are the values of each plant that I measured. Now I'm going to spend a bit more time on this than I anticipated because I want to also introduce another concept, and once you understand that, the rest is simple. So bear with me. Okay, so there I have my units. There's the mean, and the mean is very simply, they're all added together and divided by 10. I then, let me just move this up just one fraction. Okay. I then take the deviation from the mean, okay, for each value. I square them and add it together. I've got the sum of squares, okay. If you want to do that in Excel, I'm sure you all know how to do it. Why won't it? Oh, there we go. Equals sum, and you mark the blocks. Okay? You add them all together. That then is the sum of squares. I've got 10 sampling units. They're 9 degrees of freedom. Remember, there's always one less. I have the 9 degrees of freedom. So what I do is I would divide that by 9. So you'll see I have a little sheet here, calculate the mean. Well, the mean's very easy. It's equal to average. And I hope you know some of the simple Excel codes. And it does it for you automatically. Right, now you can check and see if I got the right figure in there. Okay, so you've got the mean. Calculate the variance. Well, the variance is going to be 162 divided by, it's going to be equal to that divided by 9. Ooh, and I left a bracket out. Okay, there we go. That then would be your variance. Remember, it's a square of the deviations. Now, there's a nice, easy way to do it in Excel. So why do you want to know all the maths? Just ask Excel to do it to you. You say equals VAR, and you mark your block. And okay, I did it again. Britney Spears, try again. Let me do it slowly. Equals VAR. You mark your block. And you'll see I come up with the same number. Okay. So Excel can do it for you very simply. Now the standard deviation, I said very simply, is the square root of the variance. Okay? Because we did all the calculations in squares, we want to come back to normal. Okay, so I can put in the equals SQRT, and that's why I used the abbreviations in the other. And there I have my standard deviation. Okay, but Excel is cleverer than I am. And if I put in there equals try again. STDEF, in other words, standard deviation, you'll get there now. And I'll mark my sample. And I get the same number. Okay, so when you're trying to look at the properties of a population based on the sample, you can do it very easily in Excel. You don't even need a stats program. I did talk about the coefficient of variation. Coefficient of variation is very simply standard deviation divided by the mean, which was 86.3 times 100. And what have I done there? Okay. Hopefully I did the formula correctly. And the coefficient of variation is 5%, or very close to 5%. Okay. So very easily, you can then work out the the properties of the normal curve that we discussed yesterday. And it probably takes you longer to put the data in the spreadsheet than to do the calculations. But what I want you to understand is not so much the calculations, but what these things mean. Okay? And that takes us back to essentially the graph I had there. Okay, so I just want to make sure that you understand that. Is that easy enough? Straightforward enough? Okay.
So the standard deviation 4.2 means would mean what?
The standard deviation?
We had a figure of 4.2.
That is the number of units on either side of the mean.
Right.
Okay, which would then cover 68% of the population. If I want to make that 95% of the population, I have to multiply that by the appropriate t value. Now, I haven't got the t value in front of me at the moment, but for that sample I showed you with 10, it's probably in the region of 2.2 or somewhere around there. So not 1.96 because it's a small population. So I'll take my standard deviations, which is 4, times, what did I say? 2.2. Okay, times 2. Okay, is 8. And that would be the deviation on the other side of the mean that would cover 95% of the population.
What term we will use for that corrected value?
Say again?
That corrected value, we multiplied the standard deviation with 1.96.
You find that.
Then we got another value.
Then you get another value.
What
But-
we
yeah.
termed that value?
Say again? What would be?
The term of that value, what we will call that value?
No, that would also be, it would be the standard deviation units required to cover 95% of the population. Okay, and that's essentially would be your t value at 95% probability. Okay, so you want to make sure that there's a good probability that I'm covering 95% of that population. Okay, and that value that you require there is actually the t value for what we refer to as a 95% probability, which you look up in a table that is in any stats book, on Google, or anything like that. Okay.
And which is dependent on the degrees of freedom.
And it's dependent on the degrees of freedom. So if you have more than, let's say, 120 samples or sampling units, you use 1.96 because that is big enough, you know, to be able to say with confidence, I've got 95% of the population. When the population or the number of sampling units that you use gets smaller, there's uncertainty. Because the less I sample, the less variation in the population I'm actually measuring. Okay, so there's a degree of uncertainty. So we have to increase that value to make sure that I cover the 95% of the population.
So your 1.96 comes from almost infinite degrees of freedom.
It does, yeah.
But the question he was asking, I think, was if you have a sample of size 10, the number of degrees of freedom become 9 And so
Yeah,
the
okay.
1.96 is,
Let me move to, I think I have it here. And I showed it yesterday. There was a table that you find in every book. So in other words, I had 9 degrees of freedom. I want to work at the 95% level. So we normally refer to 95%, but in the tables there, they're telling you there's actually it's a 5%. It's the missing 5%, if I can put it that way. Okay. So in other words, I've got 9, it's 2.16. It wasn't a bad guess. I'll say 2.2. Okay. 2.16 is the value then that I have to multiply the standard deviation with to cover, or to be sure that I have 95% of the population. Okay. Does that make sense? Okay. Right. Now I want to quickly, before I get to the rest of the actual analyses that we use. And this is the last concept, I promise you, and after that we'll get to analyses. Okay. But the analyses will be very easy if you understand this. Now, anybody who has done a field trial knows that we do replicates. Okay. So in other words, I don't just go in and measure the whole mass that I've planted as a single sample. We divide it up into replicates. We do that in various ways, various trial designs. We'll get to that a bit later. But what do you actually do with a replicate? You're taking your population and you're splitting it into 3 or 4 samples. So in other words, instead of measuring everybody in this room as a single sample, I may do that part there, and then I'll do that part there, and I'll do that part there, and I'll work out the average of this, and I'll work out the average of that, and the average of that, and then I'll take an average of the averages. Okay, now why do I do that? Very simply, the reason I do that is to cut out some of the variation. And if I can cut out a lot of the variation, I can get a more accurate prediction of the true population mean. Remember, I can't measure every plant in a field. So I take samples, and if I replicate the sampling instead of one big sample, and I take the average of each sample, I'm reducing variation. Okay? Now, when I started, I showed you 100 plants that I sampled for length. Now let's assume that instead of one big massive sample of 100 plants, I went and took 10 plants as my first sample. I then took another 10 plants as my second sample. And eventually my 10th sample there. 10 samples of 10 plants. Okay, exactly the same data. I'll work out a mean for each of my 10 replicates. So let's introduce the word replicate. So what I've done is I've replicated the sampling. Like you would do a field trial, you have your replicates. Okay? And why do we do that? The grand mean of this is 74, and the grand mean of that will also be 74. It won't change. Okay? But what does change, and I'm going to go back to a spreadsheet that I put together or copied and pasted earlier.